I'm going to give a couple of minutes here just for anybody who's getting between classes, but we've got a great place here. We've got a great room, and by the way, a great class. I was just so happy yesterday coming out of here with all the great questions, engagement, the fact that I'm hearing that you're exactly where I'd like you to be in terms of sort of bringing some of your knowledge from your Chem 51 or Chem 52 or other organic chemistry along, so that's great. So anyway, I'm real excited to be here, and I'm real excited to be working with you. So Stan and Sebastian and I met yesterday, and we had a chance to talk a little bit more about the homework and our plans for basically going over things in discussion sections and how we're going to do this. And it's going to be a lot like the graduate class I've taught, where people will go to the blackboard and we'll share a lot of answers and so forth. All right, we'll give it just one more moment here. Any questions to begin? All right, well, in that case, let's pick up with our discussion of nomenclature, and this is going to finish it off. And for chapter 1. And as I said last time, what I want us to be doing is not to be 100% masters of organic chemical nomenclature. I've got a book this thick, 300 and some pages, called the IUPAC Blue Book that goes ad nauseum through nomenclature. And the great thing on a lot of that is you can look it up. What I want us to do is to start to see molecules and see molecules beyond the functional groups with a little bit of alkyl group spinach thrown on that you got in sophomore organic chemistry, and see some of the beauty of them and some of the complexity. And we're going to try to do that today. And of course, we will see a lot of different classes of molecules as well, and a lot of different classes of nomenclature. So last time we were talking about bicyclic compounds and bridged bicyclic compounds. And so I think sort of as an archetype, I started with this molecule, and we talked a little bit about it. Bicyclo 3,2,1 octane. And we talked about the nomenclature a little bit, and remember I said the basic idea is we've got bridgeheads in the molecule, the two junction points, and you number around the biggest bridge, and then the next bridge, and then the next bridge. 1, 2, 3, 4, 5, 6, 7, 8, and these numbers here, ordered from biggest to smallest, represent the 3-atom bridge, the 2-atom bridge, and the 1-atom bridge. So what I want to do at this point is to juxtapose that nomenclature with that of spirocyclic compounds, and also throw in a few other, or at least one other prefix. So I'm going to give us an isomer of this molecule that also has 2 rings to it, but now instead of having the rings bridged or fused, so we call this a bridged bicyclic compound. When I showed diaza undecene at the very end of last class, we called that a fused bicyclic compound. This we quaternaryl a spirocyclic compound because you've got a quaternary juncture. You've got one ring, one carbon, one quaternary carbon with 4 substituents on it that joins the 2 rings. And it's sort of funny in spirocyclic compounds. Everything that you do in bicyclic compounds, you do opposite in spirocyclic compounds. So this compound here is called Spiro 2,5-octane. And so we go from small number to big number, small and then big. And sometimes you got to laugh at nomenclature. Some of this is arcane, some of this is funny. But you see it once, and you start to say, okay, there's at least a system to it. And then we do everything backwards. You don't start, here we started at the bridgehead and did the big chain. Here we start on the small ring, and we number around 1, 2 for the small, then to the spirocarbon 3, 4, 5, 6, 7, 8. And so if you make a derivative like so, now we're going to name this compound as a derivative of spirooctane, and more specifically, as a derivative of spiro-2,5-octane. We've got a ketone group. So remember, you call like propanone is the ketone, the 3-carbon ketone with the carbonyl at the 2 position of it. So we call this one, and it's going to be spiro 2.5 octan -4 one. Now you might look at the way I just numbered and say, what's going on here? Well, we're still numbering the smallest ring first, and we're going to try to place the carbonyl. The carbonyl is in the bigger ring, so we're going to place the carbonyl at the lowest number possible. So we just go 1, 2, 3, 4, 5, 6, 7, 8. All right, the other thing I think that this is a nice point to bring out is we talked before, and I said to you there were terms for replacing atoms, and I showed you oxa, aza, and thia. These are terms that are actually worth knowing. They roll off organic chemists' tongues. And I also cautioned you when I said oxa that we have an A in the end, and that it means an oxygen in the ring. Whoops, jeez. So for example, if we take our spirooctane example, and I put an oxygen into the ring, now we name that oxygen as oxa, so we're going to call it 1-oxa spiro 2,5. And let's give us our carbonyl just so we sort of add to our molecule and add complexity. Octan 4 one. It sort of builds on itself in terms of nomenclature. In other words, we started with a parent ring system. We identified the way we named the parent ring system. We started to modify the parent ring system. When we saw the modifications are tacked on, we continue to modify the parent ring system, and we just tack on the modification. Yeah?
Is there a reason why you added the 1 in front of the oxa?
Yeah, because we could have had the oxygen over here, in which case we would have had a different number for it, or we could have had it over here or over here. So yeah, there is.
Why is it still octan if you only have 7 carbons?
Because the parent, and we saw this last time when we went to the oxa bicyclo 2,2,1 heptene system. It's the parent system, which is that number of atoms, 8 atoms, and then it's replace 1. And these are good questions. And the bigger picture here, I'll come to you in a second, the bigger picture here is not necessarily remembering all of the nomenclature, although you'll be surprised how much you internalize without even trying. The bigger picture is seeing anatomy. It's that you take somebody in the 51A course, in the introductory sophomore course, and they're struggling to see a ketone functional group if you just draw something. That's the level of mastery. And now we're starting to see this progression of, oh yeah, we've got this ring system, it's built up of this and this. And so when you start to go to really profound molecules like morphine, which is one that I use as an example a lot in teaching, well, in teaching a molecular modeling course and teaching spectroscopy class, being able to see the molecule and its components and its shape all fit into that real inside-the-head understanding of organic chemistry.
So does that same idea apply to why it's 2,5 instead of 1,5 if there's only one?
It's the same idea, absolutely, absolutely. We started with the parent, and then we just keep, or the parent, and then we just keep modifying and modifying. Yeah.
Would anything different happen if both of the carbons on the three-membered ring were replaced with oxygen, just because the oxygens would be adjacent?
So that's a great question. So then it would be dioxa. So if we went ahead and did this, it would be 1,2-dioxa spiro 2,5-octane fluorone. And again, seeing, and again, seeing that anatomy and being able to see that anatomy is really profound, and that's essential to our thinking. So I'm going to draw a really horrible molecule based on this question. I wasn't planning on drawing this. I'm probably going to get arrested for doing this. All right, does anybody know what this really, really horrible molecule is that has these two oxygens next to it? Yeah, it's explosive. What is this? Yeah. What?
TNS?
No.
No TNS. From acetone and hydrogen peroxide.
Yeah, it's acetone and hydrogen peroxide. This is the triacetone triperoxide that's going in these suicide vests, which have been wreaking havoc with terrorists. Now, take this molecule for anatomy for a second, and we start to see a couple of things. First of all, as we saw over here, this is a peroxy linkage. In other words, you can see now, as an organic chemist, and as somebody who's been steeped in organic chemistry for 1 year, or 3/4 plus 2 lectures, you can start to see, okay, wait a second, I can understand this functionality here is an acetal. In other words, you can start to look at this and say, oh, wait a second, the anatomy of this molecule is an acetal of acetone, and it comes here, it's an acetal, right? If you have this molecule, this is an acetal of acetone and methanol, right? And you formed that by methanol plus acetone. I'll write it in the same way. I'll write it as MEOH with acid catalyst. And so you can start to say, oh, wait a second, this is an acetal of acetone and hydrogen peroxide. And that's what makes this really scary, is basically you can get these ingredients in a hardware store and a drugstore. And so this is very accessible. But being able to look at this molecule and assimilate the anatomy, being able to look at this molecule and assimilate the anatomy is what we're talking about right now. And reagents like this get used as oxidizing agents in organic chemistry. And when we come to chapter, I think it's 6 on functional group transformation, you'll learn about various reagents. I don't know if we're going to cover the, I think it's just the acetone, I think it's the monoacetone peroxide. Sebastian, do you remember the oxidizing agent from synthesis? I think it's this one. Anyway, basically, we'll start to see. But yeah, so we start to understand that anatomy, and then these reagents make sense. So I want to finish up with what I was juxtaposing here, finish up this little segment. So I cautioned that oxa is oxygen in ring. Oxo is equal to a carbonyl substituent on a ring or chain when you've got a higher priority substituent. So remember I said it goes by oxidation states. You've got alkane at the lowest oxidation state, then you've got the alcohol ether oxidation state, then you've got the ketone aldehyde oxidation state, finally the carboxylic acid oxidation state in dictating names. So just to fill things out here, and perhaps drive you crazy, or at least drive home a point, I'm going to go ahead, and this is actually really similar to an example in your textbook, and draw out this molecule. And at this point, we're naming this molecule as the carboxylic acid. And so it becomes an oxospirooctane carboxylic acid. And all of the numbering that we did before, basically putting the lowest number on the smallest chain and putting the lowest number on the substituent, and then numbering around as beyond that to give the functional groups the lowest possible number applies. And so this molecule becomes 4-oxo. Notice we're using oxo, not oxa. Spiro 2,5-octane 1-carboxylic acid. All right, so at this point, I want to move on to some polycyclic compounds, and maybe if I have time, tell you a story about cancer. So, all right, we all know benzene, right? So polycyclic, many rings, and so we'll start with polycyclic, I guess more than compounds, I'll say polycyclic aromatic hydrocarbons. So all the aromatic hydrocarbons were initially isolated from coal, well, not all, but the ones that were isolated, and there are many, were isolated from coal tar, basically taking coal from under the ground, heating the heck out of it without air, and boiling off the volatile compounds. And so as you get, so you get benzene and toluene and bigger compounds. So we've got one compound here. Anyone know the name of this compound? Naphthalene, right? You know where you can find naphthalene? Kind of. I heard somebody say it. Mothballs. So it's one of the two compounds that's widely used to pack clothes to prevent moths, or more specifically the caterpillars, the larvae, from eating particularly woolen clothes. So what I think I want to do with naphthalene is use this as a starting point to talk a little bit about numbering and then take us further through. So okay, so you number aromatic hydrocarbons, polycyclic aromatic hydrocarbons, starting in the upper right-hand ring as drawn, and generally you draw them horizontally to put as many rings horizontal as possible, and then beyond that try to put as many rings in the upper right-hand corner as possible. And so you start in the upper right, and you go round. You skip the ring fusion, so you go 1, 2, 3, 4, 5, 6, 7, 8. And then the ring fusions sort of get a lower priority because there's nothing happening. In other words, I could make 2 chloronaphthalene or 1 chloronaphthalene, but as soon as I put a chlorine on this carbon, which is fully valent, in other words, I can replace a hydrogen here, but then I break unsaturation. So I can't make a, say, chloronaphthalene at this position. It becomes a chlorohydronaphthalene. So we give a lower numbering system, and we call those 4A and 8A. So I'm going to write here and sort of jot number from top right, so you have it in your notes, as drawn. And I'll show you, as I said, it's try to draw as many rings as possible. Top right ring as drawn, and skip the junctions, just like we did with naphthalene. I guess I'll say, junctions, fusions, whatever. All right, there are 3 that probably roll off my tongue very easily as an organic chemist, and I probably embarrassingly have a better memory for molecules' name than people's names, and my memory for molecules' names isn't that great. But there are things as an organic chemist that you just see so much again and again that as I said before, they sort of become part of you if you use them or think about them on occasion. And so I'll show you 2 more polycyclic molecules that, I don't know, I mean, I couldn't imagine not being a practicing organic chemist and knowing their names. Phenanthrene and anthracene. And so all of these molecules are fully unsaturated. In other words, every carbon has, just double bonds to it, or at most 1 hydrogen to it. Anyone recognize the name anthracene? Anthrax. To my knowledge, no connection. Maybe, I don't know. But another one, anybody recognize it? Anthracite coal. There's a hard coal that has the name, I think it's called anthracite. And it basically, given that these are all originally isolated by heating the heck out of coal without air, it's not completely surprising. So keeping the same principles here, I'll just show you here for the numbering of them. This is going to come back in a moment. As I said, I want to give an example that relates to cancer. So here's our numbering here. Here's our numbering here. So 5,10 dihydroxyanthracene would have a hydroxy group at this position and a hydroxy group at this position, or 5,10 anthracene diol, you could call it. All right, the other thing we talked a little bit, and I sort of threw in as an aside, numbering these non-substitutable positions. So beyond A, you get B. So if you really care about it, this junction here becomes 4A, this one becomes 4B, and then 8A, and so on and so forth. Not super important, but something that's sort of cool and arcane. All right, at this point, I want to say it is very easy to get stressed and sort of bent out of shape because it seems that there's so many different molecules. And as I said, these are gonna, some of these, not everyone, is gonna become internal for you. And what I guess I'd also want to add is a little bit of stress is good. I mean, it makes you learn stuff and makes you say, oh, I really have to pay attention. Too much stress is bad because it just means you're going crazy here. So, I mean, right now, work the problems. You're going to read the book. You're going to internalize a lot of it. It is my plan, if we end up with anything that has names on it in the exam, and I probably will post something, basically to share with you the tables that you printed out on the exam. So, here's common names, and these are cool compounds. All right, I want to talk to you at this point about a carcinogen and also maybe give us a little bit of appreciation of some of the nomenclature of it and some of the arcane stuff that's involved. All right, so let's take as an example benzo A pyrene. And this gets us into one more example of nomenclature. All right, benzo A pyrene is really bad stuff. You heat the heck out of almost any carbonaceous material, and you get polycyclic aromatic hydrocarbons. That's what's happening in coal. It's been under the ground for hundreds of millions of years with pressure and heat. You're starting with all sorts of carbon molecules from plants and I don't know what, dinosaurs, heating and pressing on it for hundreds of millions of years, and you get graphite and pieces of graphite, smaller and smaller, like anthracene and naphthalene. Okay, benzopyrene, heat the heck out of it. It's a carcinogen in tobacco smoke. It goes right into your lungs. So I want to talk about the nomenclature here. So, okay, we've got pyrene. There's a bunch. There's about 35 polycyclic molecules that have common polycyclic aromatics that have common names. So I want to show you what benzo A pyrene is. All right, so let's draw pyrene. You can copy it there, or you can copy it from me. I'm going to start and draw naphthalene. I'm going to add a ring to naphthalene. Here's something cool. I can't add just one ring to naphthalene and keep a fully unsaturated compound. You notice I've put in my double bonds, and I've run out of room for double bonds here. But you put in one more ring, and you're up to a point where you can go ahead and have a fully unsaturated compound. So this is pyrene. We're going to number around as drawn, and you see that you have it here. So basically, as drawn, we've drawn horizontal rings, as many as possible. We'll start in the upper right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's right there on your screen as well. Now, so I'll say number is drawn. From the upper right. Now, the next piece of arcane business in nomenclature, it's all sort of cool and freaky at the same time, is we're going to letter, starting with 1 to 2, I'll say letter our edges starting with 1 to 2 and doing all. So in other words, we'll letter this edge A. That's good because I said we have benzo A pyrene. This edge B, this edge C, we're going to continue around right to position 3A, D, E, F, G, H, I, J, K, L, M, N. All right, so benzo A pyrene, then we're just going to fuse another benzene onto the A ring. So I'm going to redraw pyrene. And part of this is an exercise in us just spending a few moments to see the anatomy here. We're going to add a benzene ring onto the A ring, or onto the A edge. And so that's benzo A pyrene. Let's see. Okay, now the crazy part, and I'm going to go somewhere with this. So, okay, so then for numbering, now you reorient. And it's this principle of maximum number of fused rings horizontal, and then we start numbering from the upper right-hand ring. So maximum number of rings, 1, 2, 3. So just like anthracene, we're going to do 1, 2, 3. I'm coming here to an even nastier carcinogen. And then we're going to take the remaining 2 rings and stick them up in the upper right-hand corner. So all I've done is flip and rotate our molecule around. So that's how we orient it for numbering. And then we number from the upper right-hand ring. And that's how you number your benzo A pyrene. All right. Well, benzo A pyrene, as I said, is what you breathe in when you're one of the many carcinogens, when you breathe in hamburger smoke. I think it also tobacco smoke. I think it also forms in burned meats, but your lungs are really vulnerable to cancer. Now, your body takes big greasy objects, big greasy molecules, and it can't process them, it can't carry them, it can't excrete them when they are so greasy. So your body does what it does to process big greasy molecules. It oxidizes them with an enzyme called cytochrome P450. And so benzo A pyrene forms in your body the 7,8 diol 9,10 epoxide. Whoops. Epoxide's another word for oxyrane. Bicytochrome P450. So your body does what it tries to do to rid itself of big, greasy molecules. It oxidizes them with a heme-containing enzyme. And so we're going to draw that molecule now. And so now we know the secret of nomenclature. And I actually, until I read this book, never quite knew how one got there. And it's sort of like, oh, cool, now I know this little arcane piece of knowledge. And so we're just going to number around as we have done. And we'll come to this ring, which we said 7,8 diol. I'm going to draw, there are a couple of diastereomers that can form actually two enantiomers. I'm just going to draw one of them. I'm specifically not specifying the stereochemistry in my nomenclature. So I will just say this is one stereoisomer. And this is what gives you cancer. Anybody have any idea what this big, flat, hydrophobic region, greasy region looks like? Something related to cancer. Where does cancer start? DNA. Yeah. It intercalates. So you still have your double helix. Big, flat, greasy molecules stick themselves in between the bases. Who's had a biochem lab or anyone work with ethidium bromide? Okay, ethidium bromide is a big, fat, fluorescent dye molecule that goes into your DNA. But your body has just put a warhead on this big, flat molecule. What do you think that epoxide ring, think back to all the way to sophomore organic chemistry, to that molecule, to oxyrane. You used it for something in sophomore organic chemistry.
Would it react with the nitrogenous bases in DNA?
Exactly, it's a DNA alkylator. So a nucleophile like nitrogen reacts here, and a nucleophile like nitrogen, I believe it's reacting right over here. And what have I, hold on, I have managed, what have I managed to do? Oh, one more double bond, there we go. So benzylic position, and so it is particularly reactive. You can find X-ray crystallographic structures. People have studied this, obviously. We want to understand how cancer comes about. X-ray crystallographic structures of benzopyrene, basically intercalated in and covalently alkylated to DNA. And so that stuff is just like one of the worst carcinogens you can possibly imagine. And we're talking micrograms of this compound, because you get a whole bunch of junk when you burn tobacco. And you only get a little bit of benzopyrene, but a little bit of benzopyrene is all it takes to really mess things up with your DNA. And your lungs are so vulnerable because you've got basically tissue exposed right there for all of those organic compounds to come in. Anyway, as I said, sort of beautiful and horrible at the same time. All right, I want to talk about heterocyclic compounds. And I want to take you through a few common ones. I'm going to talk about heterocyclic compounds, monocyclic. And then I want to show you another table to make some sense of it. And so I'm just going to write out a bunch that probably roll off of Sebastian and Stan's tongue. Oxyrane, aziridine, Now, let me talk about the numbering for a second. You number from the heteroatom, so you number 1, 2, 3. So if we go ahead and we say 1-methylaziridine, this is 1-methylaziridine. If I go ahead and say, let's say, R2-methylaziridine, whoops. Then we're going to go ahead and say, okay, that means we have a methyl group on the carbon, and we're going to put that methyl group so that we have the R stereochemistry, and we'll remember, okay, there's a hydrogen here. We cite down to the bond to the hydrogen. Nitrogen, highest priority. This carbon with just 2 hydrogens and 1 carbon attached to it, and a nitrogen, higher priority than the methyl, so 1, 2, 3. So there's our R group. And there are all sorts of other names if you have a double bond, and I'm going to show you how to make sense of all this in a second, so don't worry too much. Oxyrene, that makes sense. We've got a double bond, ANE for saturated, ENE for unsaturated. Oxetane, and as I said, if you use these a lot, they roll off your tongue. Azetidine, and then just to have some fun, let's do a few variations here. So if we do a 5-membered ring with 2 oxygens, it's going to be 1,3, in the 1 and 3 position, it'll be 1,3-dioxolane. You might have seen for, as a solvent, 1,4-dioxane, and let's say, I'll give you one more example. I think we're going to see this in our chapter on synthesis where they talk about umpalung, and this is 1,3-dithiane. Yeah.
With the dioxolane, is it di-O or with an A?
Oh, dioxolane. Dioxolane.
So it doesn't follow the...
Doesn't follow it. Now, let me show you the key on all of this, and I want to put all of these into context here. So remember I told you that those tables had a lot of good stuff in them? Okay, tables 1.2 and 1.3 make sense of all of this craziness. Let me go ahead. I'll make this a little bit bigger for us. All right, making sense of all of this craziness. So you choose your atom, ox, for example, ox, 2 oxygens if there are 2 oxygens. You choose whether you have compounds containing no nitrogen or nitrogen, no nitrogen. You choose whether they're saturated or unsaturated, dioxolane. If you have, so what about that crazy oxetane but azetidine business here? Okay, compounds with oxygen get ox, compounds with nitrogen get A's, compounds containing nitrogen go under this category here, 4-membered ring, azetidine, compounds without nitrogen, oxetane here. So basically, it's just run down the table on naming them. Yeah?
With something like 1,3-dioxolane, though, why wouldn't we just call it like 1,3-dioxopentane?
You could. Certain compounds have special names. And I want you, when you're seeing all of this, take it in, also have a little bit of a laugh at this. Because some of this is funny. Some of this is funny, these arcane rules. And again, realize if I ask you anything from this, I'll give you the table. Just have worked through it once as you're working through the chapter and the homework problems. Make sure you internalize it. But it is sort of funny. Now, things get even funnier here. All right, things get even funnier because all of this, you can say, at least by some way, shape, or form, is systematic. In other words, in other words, it may not make sense that it's azetidine but oxetane, but you can walk through a system on it. These are molecules that got their names when we understood structure, or at least got their names that really stuck when we understood structure. But all of those names like phenanthrene and anthracene came from organic chemists sort of in the 19th century and maybe early 20th century, where organic chemistry was isolating stuff, figuring out, okay, it has this melting point, so it's a pure compound. When I burn it and I calculate how much CO2 and H2O are produced, I get an empirical formula of, say, C10H8. And so you say, okay, I don't know the structure of naphthalene, but I know it is C10H8. And then as understanding came along and we understood the valences of carbon, we eventually were able to piece out the structure. But a lot of these initially got the name that they were, this was the molecule that I isolated when I heat distilled anthracite coal. So, okay. So with that, there are certain monocyclic, heterocyclic compounds and all the carbocyclic ones, of course, I'm talking about have sort of, at least the 35 that I mentioned, sort of have crazy names, special names. So I'll say with special names, you can call them trivial names. These are the names that came before people knew their structure and stuck. And they just roll off the tongues of organic chemists. So for example, breaking the rules on the tables 1.2, this molecule here is called pyrrolidine, Pyrrolidine. And again, I'm going to take us back here. And again, I'll sort of take us over to this table, so don't stress too much about this. Have a little bit of laugh of history. But these are ones that also roll off of Stan's tongue and Sebastian's tongue. This molecule is called pyrrole. We're going to talk a little bit about aromaticity in the course, but I hope that you remember from sophomore organic chemistry, when you have 6 pi electrons in a ring, you have special stability of an aromatic compound. There's a lone pair on this nitrogen. That lone pair is in a p orbital, and so we get 2, 4, 6. Pyrrole is an aromatic molecule like benzene, although with about half as much resonance stabilization. It's much more reactive in electrophilic aromatic substitution, but it still behaves like an aromatic compound, not like an alkene. This molecule here is called furan. This molecule here is called thiophene. And again, most of these molecules would go back to isolation before people had systematic understanding of their structure. All right, so let's see. So I think I want to conclude with a couple of comments about unsaturation here. All right. So for unsaturation, we take a lot of these names and we note where the hydrogen is added. All right, so let's start with furan. So here's furan. We number it starting with the heteroatom, 1, 2, 3, 4, 5. And so if we add 2 hydrogens to the molecule, we come up with 2,3 dihydrofuran if we've added them across the 2 and 3 positions. If we add them across the 1 and 5 positions, we now have 2, 5. I'm sorry, across the 2 and 5 positions, we now have 2, 5 dihydrofuran. And hopefully, all of us have seen this molecule in the course of our sophomore organic chemistry. What's the name of that molecule? Tetrahydrofuran. Commonly called THF. THF is widely used as a solvent in, for example, Grignard and organolithium reactions. I think we use it widely. Who's had the Chem 160 class, by the way? Oh, okay, and we've probably used it. I'm pretty sure we use it in the Chem 160 class for certainly the first reaction is a nice aldol reaction, and I think we run it in THF. All right, last thing I want to say, rings that cannot have full unsaturation. Get, number and H to show the position. All right, so take a 6-membered ring with oxygen in it. I cannot have a neutral 6-membered ring with oxygen with 3 double bonds. I can have 3 double bonds and a positive charge on oxygen. That's called beryllium. But the only neutral molecule I can make, any neutral molecule I can make, has 1 carbon that is unsaturated. So we call this molecule 2H pyrene. Pyrene was one of those trivial names on your chart. And then so we're numbering around the ring. So it basically is 1, 2, 3, 4, 5, 6. So if I make a substituted variant of it, this would be 6-methyl 2H pyrene. By the way, if you print on your computer, you would print it with the H in italics. And just to juxtapose this, I'll show you one isomer of pyrene, of 2H pyrene. This molecule is 4H pyrene. All right. With this brief discussion and the textbook, you have a learner's permit to play with the problems. And once you play with the problems, you'll have as much of a license as you should have. Read it carefully, play with the problems, and internalize some of this stuff. And we will pick up talking about the literature. For Friday, register for SciFinder. There's a link on the website. And feel free to bring your laptop computers. We'll play around with some online resources on Friday, which should make some chaos in the class.